All right, I merged the lectures, there were two separate lectures and I merged them this morning. So my recommendation is never print the slides, read them in the computer because they are always work in progress, okay? So what I'm gonna do is we discuss a little bit about general things on classification. So I want to go back to this, one of the three potential models that we refer to, which is generative models. So as a reminder, in generative models, what we need to do is we need to build these class conditional densities. So for each class, compute P of X, come up with some prior models for each class, and then, this is very important, compute the posterior probabilities through Bayes' rule. Because we said that another way of doing this is to go directly and postulate a model for the posterior probabilities, but here what we're going to do is start with a model for P of X given Ck, start with the priors, and use Bayes' rule as you see on the equation on the bottom. So suppose we already have come up with these classes. I will discuss how to compute those later on using maximum likelihood at least. So let's say we have those, and so here's Bayes' rule. What I'm going to do is I'm rewriting this equation here by introducing this definition of alpha that effectively is the log of the joint distribution of xc1 and divided by xc2. Okay, so this definition has no particular physical meaning, but as you will see, by a simple definition, it basically allows us to write the posterior as 1 divided by 1 plus e to the minus a, and that's the sigmoid function. And you remember one of the key ideas of classification models is if you don't want to use Bayes' rule, if you don't want to do anything, you can postulate a model of the posterior directly in terms of some nonlinear function where usually a is taking some to be a linear function of x, right? So here we have computed this from Bayes' rule. There's no approximations or anything. Use this definition for alpha and the sigmoid function, and you put the two together, right? If you divide by the numerator, you rearrange, you get this to be the sigmoid, sigma of alpha. So this can be a very nice model if it comes out by accident that this alpha for a certain class of problems is a linear function of x. Right, so that's what we're looking. Can we actually make, what type of problems can we make alpha to be a linear function of x? So before I do anything, because I will, in the lecture on Tuesday, I will need this, let me give you an approximation from the sigmoid function that's very powerful. So I'm not, the proof is actually in some other lecture. You may be able to locate it on my website, but effectively, you can approximate the logistic sigmoid that you see there with what is called scale inverse probit function, which is nothing else but basically the CDF of the standard normal distribution computed at lambda a. So you remember we want to approximate sigma of a, right? And you can approximate with phi of lambda a, where lambda squared is pi over 8. And where do you get this lambda squared equal pi over 8? You get it so that the two curves have the same slope at alpha equal to 0. This is a very powerful approximation of the sigmoid that will be used in the lecture on Tuesday, and also in other lectures as we come as we move forward. So just remember, there is a nice approximation to the sigmoid function. All right, so let's go back to the Bayes' rule. So by the definition of alpha, we wrote this as sigma of alpha, and we want to figure out under which conditions basically this leads to a generalized linear model. So making alpha to be some linear function of x. All right. Before I tell you that, you may ask me, is this sort of okay? This is a nice definition. It seems we get something like a discriminant function that may be potentially a good way to do classification, but this looks like a definition for two classes. What do you do when you have many classes? Will I be able to extend these ideas? And we already have introduced this nice equation on the top, all right? So if you have multiple classes K, you can actually, again, using Bayes' rule, you can write like that, okay? And what we're gonna do is we're gonna introduce this definition, not the ratio between two classes the way we had them before. We had the ratio P of X CK divided by the joint probability for the other class. Here we don't have this because we have multiple classes, so we define alpha K to be like this, and we express the posterior as e to the alpha K divided by the summation of e to the alpha J's for all J's, okay? And this function is actually what's called the softmax function. That's what I was asking you the other day, and as I was asking, my brain froze too, okay? And I wanted to say the max function, the soft was escaping me, so I didn't say a word, okay? So this is the softmax function, and the reason it's called the softmax, it's sort of a soft approximation to the max function. So if, let's say alpha K is greater than all the other alpha J's, you can immediately see that basically this comes to be equal to 1, and all the other posteriors coming equal to 0, okay? So this is, again, for many classes, we're going to use this representation, okay, with this updated definition. But again, what we don't know yet is if, even for the two class K, if there are any simple problems where we can make this a generalized linear model. Can we find cases where alpha is really a linear function of X? I mean, if this is sigmoid is a nonlinear function of something that's nonlinear in X, right? It's not going to help anybody, okay? So we need to figure out if there is any hope there. So the answer is yes, there is hope if we actually use this conditional distributions to be Gaussian. So let's assume that for each class K, the conditional distribution for X is a Gaussian, and there is a very specific reason that in the covariance sigma you don't see a subscript K. All right, so I'm assuming that all the classes have the same covariance, because if they don't, things may get complicated, and we will see them shortly. All right, so we assume, so the means are different, but the covariance is the same. So if you compute, this was, you remember alpha was, this is the definition. There's no proof or anything else. We define alpha to be this. So if you plug in this, you know, priors, we don't do anything, so we keep them there. You plug in the conditional distributions for, let's say, the two classes. Take the logs, there's a ratio there. So this is what you get, okay? So there is an X transpose sigma minus 1x, but you notice it's canceling out. So you can immediately appreciate why we use the same sigma, because if you don't have that sigma, then alpha comes to be quadratic in X. So you don't get a linear model, okay? So if sigma is the same in all classes, basically what you get is W transpose X plus W0, which is our standard linear form. All right, so here is an example for two classes. So you can think of the two, so these are the two Gaussians that represent the class conditional distributions. All right, you put some priors, you can make them 50% equal, you know, each of them. And what you see here is using the, this probability here, the sigmoid of the linear function W transpose X plus W0, you compute the two posteriors, and you plot them. And this is a very nice plot that maybe you have not seen it for this type of things for the first time. When you compute these posteriors, it's not like you're going to take a point X and assign it to class 1 or to class 2. What you do here is you assign, you compute these probabilities, so each point is in part in class 1 and in part in class 2. So if you compute probability 0.6 for class 1, means 60% of the point belongs in class 1, 40% in class 2. Okay? So this plot, the coloring changes, and the coloring represents, for example, you can, sort of, as you know, I'm not very good with colors, so you know, this is class 1, but somewhere in between there, as the color varies, the color is assigned with weights proportional to the posteriors, so these points are somewhere in between the two classes, and here belong completely to class 2. So this is something you should learn to do for your own research, right? When you plot things, you know, say you do mixture models, things like that, you need to be able to plot points with colors that they are proportional to the posterior distributions. All right. So this, I mentioned this, when you compute W0, that's the only dependence you get on the priors of each class. And the only thing really that these priors are doing, they don't come inside the definition of W, they're basically leading to sort of parallel shifts of the decision boundaries. So the slope W doesn't change. All right, how about this model now? What do you do with when you have many classes? All right, so for many classes, we introduce the softmax function like that. So the posteriors take this form where this is our definition. Okay? So if you go and plug in a Gaussian class conditional for that, and you take the log of this and you have the log of the prior, and you keep all the terms, you basically get a quadratic term, unfortunately. You get a linear term, okay, similar to what we had before, and then you get some bias term, okay? But the quadratic term is unfortunately there in this definition. So it seems we're going to be in trouble, but if you look very carefully, we're not in trouble. Because if you take this alpha k, all right, and you plug it in inside e to the alpha k's and e to the alpha j's, what can you see is happening? So if we take e to the alpha k, right, and then summation over j's of e to the alpha j's, what is happening to this quadratic term and all the other constant terms? Plug in this on the numerator and the denominator. What is going to happen to the quadratic term? Because you remember sigma is the same in all classes. It's canceling out. Okay? So, so when you plug in this term is going to cancel from the numerator and the denominator. And so I'm actually going to redefine alpha k now without the, you remember before when we had this definition, we had this term here, minus 1/2 x transpose sigma minus 1x. So I'm going to redefine it to be just a linear model here, w transpose x plus wk0, where this is the only terms that are important. By the way, when you look at the different books, they tell you, oh, you plug in this definition, and then there's the linear model. That's not quite true, right? So alpha k comes to be not to be quadratic here, but when you plug them in there, the quadratic terms cancel out, and then you can redefine alpha k to be like that. So you don't get this directly from the Gaussian. Some terms have been cancelled out, so you can redefine alpha k to be this linear model. So we can actually work with this generalized linear model with a softmax function quite easily in many classes. So let's give you some otherwise simple looking examples. So what you have, these are the class conditional distributions, okay? And these are the posteriors over the domain drawn with different colors. And can you give me some reason why some boundaries are straight lines and why some boundaries are quadratic? From where is that coming? So I see here, I don't know what classes are. Let's call, what color is this? What is it? Light blue, you said? Light green, okay, and this is what, red? All right, so the green and the red, why is the boundary a straight line? Is this red and green? So what do they have to common? The same sigma. All right, so these two have the same sigma. So you remember the quadratic terms cancel out and you get a linear decision boundary. All right, that's what you get. But this is not the case between the red and the blue and the green and the blue. And the boundaries are actually, because they're Gaussians, they're quadratic. Okay? And, you know, in lots of problems, you're actually maybe, you know, doing this with quadratic boundaries is not an issue. Certainly it's not an issue here, okay? But we like the concept of having generalized linear models. So in this case, we do get quadratic boundaries. All right, so these models to work, what we need is we need to have the class conditional distributions, and you need to have the priors. So we are going to compute all of this information from data. So I'm going to throw at you some data that give you some points xn from little n equal to 1 to capital N, and I give you the labels of these points. I tell you point 1 is class 1, point 2 is class 1, point 2 is class 2, you know, etc. And also I'm going to put some prior distributions on its classes that I call them pi and 1 minus pi. I don't know what pi is, so we're going to compute it. But we need to have training data that you see here. And just to make things, the algebra easy, I'm going to define the target values to be 1 if I'm in class 1 and 0 if I'm in class 2. As I told you, depending on the problem, sometimes I may call the labels 1 and minus 1, you know, depending on what the algebra looks like. Here the labels are 1 and 0. Okay, it makes no difference for you, but it may make the analysis simpler if we define the labels like that. All right, so we're going to have to use this information to compute things like the mean and the covariance and all of these, you know, and pi. We cannot just assume and hope that somehow arbitrary assumptions are going to work. So would you agree with me? So let me just go directly to save us time. That the likelihood looks like this. I want you to carefully look at it and tell me yes or no. Right, so I have capital N data points, okay? And remember, some of these data points either would be in class 1, where the label is 1, or would be in class 2, where the label is 0. So this first term is for which points? The points that belong to what class? I mean, this, you know, if tau is 0, right, they belong to class 2, this is 1, so it doesn't contribute. If tau is equal to 1, they belong to class 1, and the joint distribution is the conditional of x given the class 1, and I represent this given the mean and the covariance of class 1, times the prior. Right? Yes? Yes. All right. And the same thing for the second class. So in the second class, if Tn equal to 0, right, is equal to 1, okay? So this is what contributes from data in the second class. So the prior is 1 minus p, and the conditional distribution of x given the class labels is basically this Gaussian, okay? So the likelihood looks like this. So we're going to take the log likelihood and try to maximize. And the algebra actually is more or less like working with a simple doing MLE of a Gaussian, so it will not be very complicated. So, so let's compute first pi. So we have a pi to this power here and 1 minus pi to that power. If you take logs, you get something like this. And if you take the derivative with respect to pi and you set it equal to 0, in 0 calculations, you get that pi is summation of Tn divided by n. And if you remember, the labels are either 1 or 0. So if in your data N1 data points are in class 1 and N2 in class 2, would you agree with me that this is what you get? N is equal N1 plus N2, and the summations of Tn will come from class 1 because the label, you remember, is 1 and 0. So it would be N1 over N1 plus N2. The common sense answer, right? I mean, you didn't have to do MLE. You just take the portion of the points that they're in class 1 and you call this pi. Okay? You can extend this calculation, by the way, to multi-class for pi, and the answer is the same, right? So it doesn't really matter if you have 1 class or 10 classes. Pi k, if you have, let's say, capital K classes for class little k, is nk over n. Okay, the algebra it's a little bit bullet more involved, but it's the same. So back to our problem here. We need to compute mu1, we need to compute mu2 and sigma. So let's take derivatives with respect to mu1. Only the first term gives contributions. So you can see if you take logs, you have this becomes summation, Tn of log of this Gaussian. You expand the Gaussian, mu1 comes in the exponent, you write this explicitly, and you take derivatives with respect to mu1 equal to 0, and the answer basically is this. Does the answer make sense to you? So you remember the labels again are 1 and 0. So what is this summation? What contributes to this summation? Only the points that belong to what class? Only the points that belong to class 1, right? Because for class 2, the labels T are equal to 0. So this tells you that the mean of class 1 is what? The mean of the points that they are in class 1. Right? Yes? And similarly here, take all the points in class 2, take the mean of them, that's mu2. So again, you don't really have to do any more of this type of probabilistic optimization because the answer is the obvious answer, simple counts. You don't really have to solve, and that's why a lot of people like these generative models because you will see on Tuesday when you work with discriminative models, you really have to solve a hard stochastic optimization problem. This is not the case with the generative models. Now, the calculation of sigma is a little bit more involved, but for those who have done by hand the calculation, the MLE for a multivariate Gaussian, they know there is these problems are trivial. So what you need to do is take the logs and take derivatives with respect to sigma. So where are the contributions of sigma? Come from the normalization factor, right? So you have the determinant of sigma from this Gaussian and this Gaussian, okay, the second term, and then you have from the exponential, you have this term and that term. Now, these two terms with the determinant of sigma combined together, they give you this, right? The n and the n will cancel, so you have summation of ones, so you will get an n. And then you have to do the standard trick that you do with this type of calculations, which is what trick? What trick do you do when you do MLE for the covariance matrix? So if you want to compute, derivatives here, right? So what's the trick you do? So this is a scalar, right? So you write this whole product there, you write as a trace, even though the trace of a scalar is the scalar, but when you have trace of A times B, this is equal to trace of B times A. So actually, with rearrangement of this term and adding with this term, you can actually write the whole thing as trace of sigma minus 1 times this matrix S, right? That is a weighted average of the data covariances in class 1 and class 2. Here is the definition. Okay? Again, what you need to do is write this as trace, move the X transpose to the right, move this X transpose to the right, so you're going to have sigma minus 1 times this term, and then sigma minus 1 times that term, okay? And I remind you that this summation here is non-zero only for points in class 1, right? That's why you get S1. And this summation is only non-zero for points in class 2, okay? So when you do this, you get a log likelihood that looks like this, which is identical to the log likelihood that you get when you do the MLE for a single multivariate Gaussian. And again, you can go and consult the textbooks or the notes from another here. So when you take derivatives now of this, the formulas are given, I think even on these slides potentially, or if you look at Bishop's appendix, you will see how to take derivatives of the trace with respect to sigma. And the answer is equal to what? So here's the answer. Sigma equal to this, okay? Where S1 and S2 is like that. So we're done, right? So we basically have the pi, we have the means, and we have the MLE of the covariance. And again, MLE is not the end of the day, but we have said it's not good. It's like least squares, and it's not robust to outliers, so that's not very good. If it happens that your conditional distributions, they're not Gaussians, right? But they are, if you are talking about discrete distributions, so maybe you have a problem where these class condition distributions are for discrete variables. So we have, d futures, if you like. So xi for each future can take the value 1 or 0. And mu of ki, right, is the future I in class K, is the probability that the future I in class K will be on, will be equal to 1. Okay? You notice the way that this is written, it assumes the classical naive Bayes assumption that says that given the class labels, the futures basically are independent. Okay? So what I'm able here to do is, I'm able to write this as a product over its future, and this is basically Bernoulli distribution. Okay, but if you write something like that, before we had the means and the covariance of the Gaussians to compute. Now we actually what we have to do is we have to compute this mu ki for each class K for each future I. And it comes out that the problem actually is not very difficult, because if you if you go back to our definition of this alpha case, you remember, so in this case, right, we said that we assumed that we have many classes just to make it interesting. So the definition of alpha k was the log of the joint distribution of x and ck. You plug in this and you keep the priors. You basically immediately can see that the alpha k's that you get are linear functions in x. So really what you get is you get a generalized linear model. So if you have two classes, you get the sigmoid of this alpha. If you have many classes, you get the softmax defined from the alphas. Okay? One way or another, if it's a Gaussian or if it's a Bernoulli distribution with this naive Bayes assumption, they are all generalized linear problems. And the good news are the following, that somehow it doesn't have to be a Gaussian, the conditional distribution doesn't have to be Bernoulli. If you have any conditional distribution, class conditional, that follows in the exponential family, right? And I remind you what the exponential family is. You can go in the notes, read what is there, right? I'm just going to go rapidly through it. But if you go in the notes, you figure out that the model that you get leads to a linear alpha. Okay? So if you have two classes, right, and the conditional distributions are any distributions from the exponential family, you can use the sigmoid of alpha, where alpha is a linear function of x. So the boundaries basically are the separation boundaries between the classes are hyperplanes. Okay? Again, there's nothing in the slides, just generalizations. I'm just saying you can apply these ideas to many, many different distributions from the exponential family. I'm going to bypass the slide. I edited it this morning. There is an information theoretic approach to these things that, so I'm not going to put the slide because maybe it is not in the spirit of this class, but let me just say, right, if you think of, if I can go back to, for example, if you think of this model that we got for different, for Gaussians and Bernoulli distributions for the condition, for these class condition distributions, what you have is, you have some linear functions of the input x, right? And then at the end of the day, you throw a sigmoid to make these linear functions probabilities from 0 to 1. So you can think of implementing this in some complex way, these linear dependencies with a neural network maybe, with lots of hidden layers, and simply at the end of the process, you throw some nonlinearity that maps you from 0 to 1, and there are the posterior distributions. So it comes out actually that you can pose this whole problem also as a KEL minimization problem, but effectively, it leads to generalization of what I just showed you, so you don't need to know for this course much more. Okay, what slide is that? 74. Okay, so let me go to slide 85. I want to give you a little bit of introduction to stochastic optimization. So when we do this discriminative models on Tuesday, we can apply them for logistic regression. So these ideas that you hear now, even though we may spend only 10 minutes to introduce them, they're extremely general and extremely powerful, so you need really to understand them, okay? So imagine that you have to find some parameter, you have to minimize a function with respect to some parameters theta. And I will give you specific examples in a second, right? I mean, that's what we did with the maximum likelihood, that's what we do with map estimation, minimizing loss functions, etc. But now we assume that this function is written as a summation of these functions that have an index I there, and these functions that you see here are computed separately for each data point. So I'm referring here to, in the context of training something, right? When you train and you try to minimize a loss function, you can think of the loss function computed one data point at a time. So this is what I imply here. F of theta and Zi is not f of theta, right? It is, if you like, some noisy version of f of theta where data point I comes. So this is, we will see this on the slide to come. This is really an expectation of some noisy representation of f of theta, if you like. Okay? But the point here is it is computed for n refers to each of the training data points. Okay? So for example, if you think of maximizing, so this here we minimize this function. So you can think that the function that you want to minimize is really minus the log likelihood, right? We usually maximize the log likelihood, so you can think of f of theta comma Ci being minus the log likelihood, right? And usually the log likelihood, if you think that one data point comes at a time, it fits in this category, right? So the idea here is we're going to throw one point at a time because we want to do this optimization sequentially, okay? So maximizing the log likelihood, right, fits in this problem. And similarly, if you try to minimize the loss function one data point at a time, we have seen this when we discussed about decision making. So you have a model, right? And you have some measurements. You define some L2 or L1 norm for the loss function. that fits in nicely with what I have up there. All right, so how then, for a problem that has this form, how do you compute the parameters? You compute the parameters using gradient descent, and this is the general form, all right? So you basically use the gradient of these noisy representations of your function, okay? And this is the most general formula that I give you at the top, right? So here we have summation over n, so I'm preserving this. But in reality, the way that this equation is going to be implemented is the way you see on the equation on the bottom. You're going to use basically updates using one data point at a time, okay? And eta is what is called the learning rate in these problems. Regardless of what you select, okay? So where you can read the literature on what you use as eta, but the key point here is one data point at a time. So if you do, let's say, maximal likelihood estimation, and I think I already had given you even expressions for this, possibly in an earlier lecture, you can do MLE estimation of the mean square error where you only compute the gradient, all right, for the contribution, the gradient from one data point at a time. Okay? So you don't take all the data, throw them together, right? You can do one data point at a time. Of course, if you don't want one data point at a time, instead of using all the data, you can use mini batches of data, way smaller than n, and this will work as well. And once you do a few iterations, you can either take a running average of the parameters, or you can use an averaging the way you see here, and there are many formulas like that that may or may not work for your individual problem. All right, so let's introduce a very sort of standard algorithm that was literally developed in 1951, all right? And now it is basically in the heart of doing stochastic optimization in deep learning, neural networks, everywhere, okay? So this algorithm goes with the name Robbins Monro algorithm, and it's sort of not very much different from what you saw before. So what you saw before, it was 1 over n of the evaluation of this for each data point. So now I have it sort of in a more rigorous way, and I say that 1 over n that I had before is really the expectation of this. You see that? Right? So effectively, again, you want to minimize this function f, but really the only thing that you have access to, the only thing that you can compute is some noisy representation of f. And because it's a noisy representation, you really need to eventually take an expectation of that, okay? But we cannot work with f of theta, but we can work with f of theta and z, okay? And and that's why you see the expectation there. So this algorithm originally, the way it was proposed, it was not for doing optimization problems, but it was to find the root of noisy functions. So basically, actually, what you see here, I cut it and pasted from the original paper. So very rapidly, what the definition is, you have a function m of theta, and you want to find the root of this equation. So m of theta equal to some alpha. All right, you want to find the zero of that equation. Unfortunately, you don't have access to m of theta, but you have access to some noisy representation of m of theta, which you call n of theta. So the expectation of n of theta is equal to m of theta. So the whole algorithm is how do you use this noisy representation of your function of interest, here n of theta, to do stochastic optimization and iteratively converge to the root that you want to compute. So this is basically what you see here is the Robbins-Monro algorithm with learning rate eta of n. The subscript there n implies that in principle the learning rate has to adapt with iterations or with time, okay? But there are certain conditions that need to be satisfied as we change the learning rate. These are standard. A typical choice is to take alpha over n for some positive alpha. It satisfies basically then automatically these conditions. And again, the only thing you need to remember is one data point at a time, and the gradients and everything are computed with noisy representations of the actual function. So what is nice with these methods is that where other methods may fail when you have noisy calculations, this method seems to work. Okay, and people will ask, is there any fundamental proof that this will converge or it will converge to the unique solution? The answer is no. Okay, but the fact is that these methods work very well for non-convex optimization problems. Okay, and a lot of the problems in inference and learning are non-convex optimization problems. So here's another choice basically for the parameters. Again, if you search in the literature different papers, they will give you a lot of things, and I'm sure if you use packages for doing stochastic optimization, they must be giving you a lot of choices on the learning rates. If your parameter vector, if your parameters is high dimensional as a vector, right? You really want not to compute all the parameters with the same way, but you want sort of to adjust this the step size of the calculations and the gradients in some ways following the curvature of the loss function. So what you see here is an updated, if you like, Robbins Monro algorithm, where you update at step k+1 each parameter separately, and there is a correction here that accounts for the previous gradients with respect to this parameter. So the idea here is if you have extreme suddenly parameter updates that take you from one value to something very different, these updates will be dampened. And when you have very infinitesimal updates, then the learning rate using the previous gradients will be enhanced. Okay, so there is, I know there is a number of recent review papers on this topic, so you can search them and look for them and try to read more details. But the amazing thing is that these techniques were introduced in the 50s, and people are using them now, and sort of they have revolutionized the way we do large-scale non-convex optimization problems. All right, so let me give you an example that something we already have seen. It's a little bit out of the context of classification, but because I will use these ideas for classification, hopefully in the next 5 minutes, I want to remind you the way we were doing regression. So the only difference here, I put, you remember when we were doing linear regression, the regression function was W transpose X, okay? You remember the error function, the mean square error? It was basically summation over I of W transpose Xi minus Yi squared, right? So if you take derivatives with respect to each of these W's, what will you get? In this case, derivatives with respect to theta, you will get Xi times that, right? This is scalar times Xi. So if you do learning of the MLE estimates for regression using Robbins Monro, effectively the parameters at k+1 would be the parameters at k minus this gradient here, right, which is xk times theta transpose xk, which is the prediction of your model at point xk minus the actual training label that you had, which is yk. Okay, so you notice here what drives this iterative calculation, the updates of theta, is really the error you commit at each point. Okay, but it's multiplied by the point xk itself. So in some sense, the formula that you see there, it's sort of universal. It comes up in regression, classification, and it comes up actually in generalized linear models. So when I'm going to give you a lecture or two on extending regression and classification to very general models, you will see the updates formulas, they're practically identical. So if you understand this, you will understand everything else, okay? So that's the gradient with respect to the parameters. So Robbins, Monro for regression, and the algorithm actually in machine learning comes with the name LMS, least mean squares algorithm, okay? This is for calculating the MLE estimate, but obviously you can generalize to other things as well. All right, so let me, we have 5 minutes, so I'm gonna go rapidly to give you, as an introduction before we do on Tuesday these more difficult optimization problems, I'm gonna try to give you an extremely trivial and a very early application of Robbins Monro algorithm to a learning problem. So let's assume that we have binary classification, t equal +1 for class 1. These are the labels, t equal -1 for class 2. Okay? And basically, we have a generalized linear model. The futures here include the bias, all right? So basically, I even allow a transformation of the futures. So instead of having just x, I can have some function of x. And you know, again, when you calculate this function, if the alpha is greater than 0, you assign x to class 1. If alpha is less than 0, you assign it to class 2. Okay? So I want to use the Robbins Monro algorithm for this problem. So here's the tricky idea to make this to fit in on the Robbins Monro framework. We're going to assume that points x will belong to class C1 when W transpose phi greater than 0. That's what I told you a few seconds ago, right? So when that coefficient A at x1 is positive, is class 1, and when W transpose phi of xn is less than 0, that's class 2, okay? And what I'm going to do is I'm going to assign 0 error to points that are correctly classified, but points that are misclassified, I am going to assign an error that looks like this. So think about, right? Say point T1, let's say, belongs to class 1. So what is T1 equal then? If it belongs to class 1? 1. And what is W transpose phi if I have misclassified this point? If I misclassify this point, it's negative. Right? So negative and negative, all right, and this one, I'm going to get an error. You see that? So the error basically that I'm going to consider is W transpose phi, which is scalar, times Tn, but only for the misclassified points. Okay? Only for the misclassified points. So if a point is classified correctly, there is no error. Okay? So the summation here is over the misclassified points. All right. So this is a fantastic demonstration of Robbins Monro, because if the error function that you want to minimize looks like this, so the updates of the parameters basically is the previous parameters minus the learning rate times the gradient, one misclassified point at a time. So if you take derivatives of this with respect to what W, what you get phi n times Tn. You agree? Because we will be updating one point at a time, right? So the contribution from point n would be, if you take the derivatives, right, there's a minus and a minus there, would be eta times phi n Tn. So for simplicity, let's take eta to be equal to 1. Okay? So the updates equal the previous values of parameters plus phi n times Tn. So if a point is in class 1, all right, and is misclassified, how do I update according to this formula? What do I need to do? So if a point n is in class 1, has labeled Tn equal to 1, and it's mislabeled, I mean, my algorithm is misclassified. So according to this, I would update the parameter Wt by doing what? By adding what? If Tn equal to 1. By adding phi n. And remember, phi n is here like xn, right? But it's a function of xn. I make it even more general. So basically, if a point is misclassified for being, it's in class 1, but it belongs to class 2, then I'm going to have to go and add phi n. And similarly, if a point is in class 2, but the model says I predict class 1, then I'm going to have to subtract phi n. Right? So in practice, here's how the algorithm looks like. Let's say that the vector W that we have at this time is this, I suppose, black vector there, all right? And so this is class 1, all right, on the bottom. Class 2, the blue class is on the top. So I am looking now at this point, and this point is misclassified, right? It belongs, it says, to the blue class, even though it's a red point, okay? So what do I need to do? So this point belongs to what class? To class 1. So what do I need to do to W? The model says it belongs to the blue class, which is class 2, but really this point belongs to class 1 because it's this training data, right? These are real labels. So what do I need to do according to this equation? Say it again. Add basically, add basically the location of that point, because actually this plot is done in the future space of phi of x, okay? So basically what I need to do is add to this vector, this vector that corresponds to this misclassified point. So basically this is my W plus this, and then I get a new W that looks like this.